Hello and welcome to an online version of your first tutorial for operating systems. Since we had a snow day today, I decided to make this video. Hopefully it will cover some material that you'll find useful for creating your linked lists. So I included this introduction picture that features Ken Thompson and Dennis Ritchie, who are the co-creators of both the C programming language and the Unix operating system. And both of those form a foundation for later operating systems and programming languages, and we're focusing a lot on them in this class, so I thought it was an appropriate picture to show. So we all use operating systems. All of our computers and devices use them. Some of the most common desktop versions are Windows, Mac OS, and Linux. As well, we have cell phone operating systems like Android and iOS, and also some for servers and workstations such as Solaris. And so since they each have different applications and intended uses for the end user, they all have different design considerations. And so a lot of the design of operating systems is about considering these factors and finding the best solution given the costs and trade-offs of these decisions. So computer science is a relatively new field. Computers have only really existed since the late 1940s. And in the early days, if you wanted to write a program, you would have to write it out in instructions in machine code. And this was very slow, tedious, and error-prone. For example, some of the earliest programs were written on punch cards that you had to manually feed into a machine in the correct order. And of course, if you dropped them all, you'd have to reorder them, and it was just it was kind of a nightmare to use. So at this time, computers were very expensive, and so if you were a programmer, you would have to book a time slot in order to use a big mainframe shared system, and then it would be used between multiple users, and so someone would be responsible for scheduling all of these users and programs to be run on the system. So eventually, beginning in the 1960s and 70s, people began to think about more efficient ways of sharing these computational resources between users. People wanted to create a way to run user programs that allowed for sharing and efficient use of hardware resources without having to worry about implementing the code for this every time they wrote a program. And this eventually led to the idea of operating systems. So we can say that an operating system provides an efficient and easy-to-use platform for the execution of user programs. As programmers, we want to focus on solving problems. We don't want to write everything from scratch every time. So a lot of computer science is about building layers of abstraction to make this easier. An operating system acts as an intermediary between user-level programs and the system hardware. User-level programs have to request the operating system to perform operations on their behalf. These operations are called system calls, and this protects the system from errant or malicious programs. So as I said before, there's many different operating systems, and they have many costs and trade-offs associated with their intended uses. There's no real universal definition for what an operating system is, but there's usually a part of it that's referred to as the kernel, and this is a program that is always running on the system. So it's always running in the background on your system and managing access to the hardware resources and scheduling processes. And on top of this kernel, there may be other system programs and application programs. So in this class, you're going to be completing 3 assignments, and they're all going to be graded on the Linux servers at UVic. So I recommend that you develop your programs through either on the servers or through a terminal and SSH into the server. That way you know that the program is definitely going to run on the system. It's also a good experience to do this. So on Linux, it's a very simple process, and the same on Mac. If you open up your terminal, you can just type SSH, your UVic username, at linux.csc.uvic.ca. If you're on Windows, you can use a command line program called PuTTY that allows you to SSH into the server as well. And if you follow this link, which will be provided in the posted slides, you can find a tutorial on how to do this. Since this class is very large, we can't take the time to make sure that everybody's code compiles ourselves. You're responsible for this, so if your code doesn't run on the servers, you're out of luck. So if you're developing through SSH through a terminal, I recommend using Vim. And if you follow this link, you can get a graphical cheat sheet that will give you good keyboard shortcuts to use in Vim. And if you learn these gradually, you'll become a pro in no time. So why do we want to program in C? Nowadays we have higher level languages such as Java and Python. But in the old days, people used to program mostly in assembly language. It was very low level, and they had to say exactly what byte to load out of memory, put into a register, and then load it from a register back out to memory. So it was a very tedious and slow-going process. And even the earliest operating systems were actually written in assembly. But the C programming language came along, and it was designed with the purpose of developing the Unix operating system. So what C does is it allows you to manage memory. It allows you to write to memory, but it's also a little bit higher level than assembly language. It's got a relatively compact and simple syntax and grammar. And if you've used C++, C# or Java, you'll find it's very familiar. Most of the constructs such as for loops, while loops, how you declare a function, how you declare variables, it's basically the same as Java, except for C is a compiled language, and it is not object-oriented, meaning that it has no classes. So your assignments are intended to give you an insight into the design of operating systems and the costs and trade-offs that have to be made when doing so. So like I said, the core of the C language is very compact, and it's just another step above assembly language. The language must be turned into machine instructions by a compiler, and it consists of primitive data types such as chars, ints, floats, doubles, shorts, etc. And these each define a certain length of data. For example, a char is typically 1 byte. An integer could be 4 bytes. It depends on the architecture of the system, how long the other data types are. But a char is 1 byte in all cases, which means it stores the values of 0 through 255 when it's unsigned, meaning that it's always positive. And when it's signed, it stores from -128 up to +127. The loops, functions, if-else statements are very similar to Java. I'll show you that later on in the video. And we also have things like switch statements. The array declarations are similar to Java as well. A difference is that in C we use something called the C standard library a lot, which we have to declare at the start of our programs using include statements. And then inside of the C standard library, there are system calls. And these are where you request the OS, the operating system, to perform actions on your behalf. So in most cases, these syscalls are encapsulated inside the API functions of the library. But in some cases, you do call them directly. So the POSIX standard, Portable Operating System Interface, is a set of standard libraries for Unix-based operating systems. If you're programming in on Windows at a lower level, you typically use the Win32 API, which is quite different, but a lot of the concepts are similar. So when we run a program on a computer, we typically load in data from a hard drive into RAM, which means that we have secondary storage, which is the hard drive, and we have code, which is written instructions, and this is loaded into RAM and executed by the CPU. So when an operating system does this, it creates an address space for each process. So on the right-hand side, we can see the process address space. We can say that a process is an instance of a program that is in execution on the system. This means that the program is being run. It's a dynamic occurrence of a program. And a program is just a set of instructions stored somewhere, usually on disk. So when a process is running, the program counter will step through the instructions and execute them. At the same time, the operating system schedules processes so that they all have access to the CPU at some point. And then they'll be, I like to think of them as being juggled. So they're just rapidly swapped in and out of access to the CPU. So for instance, one might be running and then it requests that it loads in from disk, and this will take a very long time. So it'll be descheduled and sent on a waiting queue, and then some other process will run. So for instance, if I want to move my mouse cursor around, we want the response to be instantaneous. So that means that we're rapidly switching between processes. So it gives you the illusion that things are happening all at once. On newer computers, they often are, because we have multiple CPUs and multiple cores. But even before that, we had the illusion of things occurring at the same time because of process scheduling. But back to the point of the address space. While a process executes function calls, the input arguments to a function are passed in through the stack. So as functions are called, the stack grows and shrinks, and it shrinks when they return. So if you have, for instance, infinite recursion, this is what leads to a stack overflow, because the stack will just keep on growing because you keep on adding values to the stack as you go deeper and deeper into the recursion. So this is the purpose of the stack. It's to store values temporarily and then pop them off again while executing. The heap is used for dynamically allocated memory. So if you want to, for instance, if you're reading in some data into an array and you don't know how long the data is, and you might need to change the size at runtime, you can request through a call to the operating system for malloc that it will allocate you space on the heap. And then you'll get some pointer which stores the address of this memory on the heap as a return from malloc. So in C programming, you're responsible for managing this memory allocation and deallocation. So you want to request some heap storage, and when you're done with it, you want to free it up. So we also have global and static variables, which are outside of any functions, even the main function. So any global variables are stored in the data segment of the address space of the process. So as I just mentioned, we have the idea of memory allocation. When variables are passed to a function in C, they're passed by value. This means that you pass a copy of the variable, not the actual variable. So for instance, if you're inside a function, you can't change the value of a variable that's passed as an argument and have it change in the function that you called it from. It only changes within the function. This is because of the scope and because of the stack. But we can allocate memory on the heap inside of a function, pass back a pointer to it, because this is just, if we get a pointer to some allocated memory on the heap, it's still there when we return from the function. So if we have a pointer to it, we can access it. So this is okay. But if we are inside of a function and we create a variable that is not used through malloc, and we pass it back, then this will be pointed to some place on the stack that no longer exists. So you should never do this. You should never allocate variables in a function and pass them back unless they're done through malloc or alloc and you pass back a pointer. I hope that's clear. Maybe I didn't do the best job of explaining that. Most of this slide is just going over what I just explained. Yeah, the use of malloc and alloc and free are they're actually system calls that are requesting the operating system to provide your process with more memory at runtime. And it's important to think about, if we allocate memory using malloc, then we have to free it. If we don't free it, then your heap will grow very large and you might not be using everything in it, and then you'll get a stack heap collision as well. So this is the reason for freeing it. So it might not be an issue in smaller programs, but if your program is running for a very long time and you never deallocate the memory, then you'll get a memory leak. So we have to think about this in C programming. So something that we have in the C programming language are structures, and this is a way to combine different data types into one object. It's like a bin for storing different types of data items. So they aggregate the storage of multiple data items, and these can be different data types. You could have an integer, a character, a string, and you put them all together, and then you can access them and change them. You can think of them as like a class in Java, but without any methods. So it's like the member variables of a class, and you can get the value and you can set the value. So the operating system has to keep track of the information about a process, and this is inside a process control block, and this can be implemented as a structure. We could also implement a database or linked list or a tree. It's just a way to store multiple different types of data inside of one object. So it's like a bin you throw everything into, and you can get it out or you can put it back in. You can change it. So this is an example of a struct. Here we're creating a struct called university that contains a character called name and an integer called year established. So if we want to create a struct that is on the stack, then we create it this way. So we're saying struct, which is the type, and then we're saying, well, it's struct university is the type, and we're calling it UVic, and then we're saying dot name, which refers to this, is University of Victoria, dot year established is equal to 1963. You notice that the dot notation is similar to how classes are used in other programming languages. Here we have another way of declaring a node, and we're using the type def. So type def is a keyword in C that allows us to create our own types. So if I said I wanted to create type def byte char, I could create my own data type called byte that's really just a char. So in this case, I'm creating a struct node and calling it node. So this allows us to, instead of typing struct university each time or struct node, we can just say node, my node. So it's just a way of writing less, really. And here again, we're allocating on the stack. So I'm referring to dot data here is 5, dot next is null, dot previous is null. And this is how you would implement a node in a doubly linked list. And you could even, instead of having your integer data, you could have a struct within your struct that stores whatever you really want it to. Depends on what you're making. Another way of doing it is to use heap allocation for the struct. So in this case, we're calling malloc. We're requesting the operating system to give us memory on the heap. So in this case, we return a pointer. So we're saying my node is a variable which stores an address to a node. So then my node stores the address of this struct in the heap. And then in the case where we've dynamically allocated a struct on the heap, we don't use the dot notation. We use this arrow notation to access the member variables. So I'm just saying my node, I've created a node of this type, and I'm just saying the data is 6. And I'm saying next is equal to my node 1, which means that this is pointing to this node. It's storing the address of this node because this is a pointer to a struct node. It stores the address of a node. And we're using this symbol to say that we get the address of my node. And then in this case, we're setting my node next to be null, which means it doesn't point anywhere. So then here we're just printing out some information. So since this is this is allocated on the stack, we use the dot notation, and this is allocated on the heap, we use the arrow notation. So I just talked about pointers, and I think it's important that we go through some more related to that. So we can say that a pointer is a variable which stores an address to a data type. So if we declare int star num, we're saying that num is a variable which stores an address to an integer. So we can think of memory as just a big array. We don't want to think about anything too complicated here, like virtual memory or even the process's address space. We're just thinking of the most basic way of thinking about memory. So if this is an address in memory, then if this was the address of a pointer variable, the value here would just be another address. So we might have the address of this stored in here, which just means this points to this address space. So in this case, we have char star p, and we see that p is a variable which stores an address to a character. If we have a variable and we want to get the address, then we just use the ampersand character. So in the case where we've declared an integer called c with value 5, then if we want to get the address where this is stored, we use the ampersand character. So since we already have this pointer to an integer here, num is a variable which stores an address to an integer, we can get the address of c and store it in num. So we're saying num now stores the address of c. So now num points to the same address of c. I hope that's clear. I will explain more, I think, with some more examples. There's also a way we can access the value that's stored, that's referenced by a pointer, by dereferencing the pointer, it's called. I find this a little bit confusing, but dereferencing just means accessing the value that's stored at that address. So if a pointer stores an address, then we access the value that's stored at the address that it points to. So here we're saying the value stored at address. This is just a way of printf saying this is a pointer. So num is a pointer to an integer. It's a variable which stores an address to an integer. So this is an address, and we're saying the value stored at this address is 5. And we're dereferencing it by using star num. So it's a little bit confusing that it uses the star symbol in both places, but when you are creating the variable, you're saying this is a variable which stores an address to an int, and then when you're using star here, you're saying I want to get the value that's stored at that address. That's dereferencing the pointer. So I think you've already been working with linked list, and hopefully you've got some previous experience with them. Many operating system components are implemented using simple data structures like queues, stacks, and linked lists. For example, the scheduler maintains lists of ready, waiting, and running processes, and it adds processes and removes processes from these lists as they execute on the system or wait for I/O. So linked lists are used to store data that is non-contiguous in memory. So if, for example, we have allocated memory on the heap, we don't know where this actually is. It might be in many different locations. It's not like an array, which in an array, the values are stored one after the other in memory. So it means it's contiguous. But linked lists are non-contiguous. So we have to have some pointer that points to where it is in memory. So in a linked list, it consists of nodes, and these are made up of data and some link to the next node. So we can have doubly or singly linked lists. So doubly just means it points to the node behind and ahead of it in the list, and in a single linked list, it's usually just the node that comes next in the list. So linked lists allow for the dynamic addition and deletion of nodes at runtime. Unless you use resizing of an array, they're typically static, which means you have to declare the size before the program is run. But lists allow us to change this while the program is running. So in C, we can implement nodes as structs, and we can use pointers to link these structs together. So your warm-up assignment has been to implement a linked list in C, and hopefully this will help solidify your understanding of pointers in C. So here are some links to useful resources. They'll be provided in the slides as well. And I'm going to do a demo of writing some basic linked list functions in C. Okay, so now I'm going to do a demo of writing some of the basic functions of a linked list in C. So I'm here on Mac OS and I want to SSH into the UVic server. So I'm going to say SSH my UVic username at linux.csc.uvic.ca. I have two windows open because it's nice to compile in one window and write code in the other. There might be a better way to do it in Vim, but still learning, so best thing is to just make it up as you go along. So I'm here in my home directory. If I type ls-la, this is running a program called ls with the command line parameter -la, which means list all. So as you can see, it just lists the contents of my home directory. But I want to go to the desktop, and I have a folder there called 360. I want to make a directory. I'm going to call it Tutorial1. Oh, I already have one, but I'm going to delete it. So I say rm-r, which is a recursive delete, which you have to use if you're deleting a directory. So I'm going to delete it. I didn't need to do that, but it's actually useful to show you guys. So I'm going to make a directory, and then I'm going to go into it. So now in my other window, I just want to navigate to that. And if I want to autocomplete or see the contents of my command, I can just press the tab key and it will list what's in the directory, which is a handy way of seeing where you're going. So I can do that. And now I have both in the same directory. So I'm going to just show you guys something about the C preprocessor. So I'm going to start by saying vim linklist.c, which means I'm just running the program vim. It's a command line program, and I'm going to give it the argument linklist.c. So that means it creates a file called linklist.c when I write in vim. So I'm going to open it up. So what's the simplest program we can write? You might be thinking hello world, but we're going to go even simpler. So we're just going to say int main return. So that's the simplest program you can write in C. And I want to show you guys the output of the C preprocessor. So I'm going to say GCC, which is the GNU C compiler. So it's just a program that we're looking up on the shell. I'm just going to say -o, which means output, and ll.text. Actually, before I say .o, I have to say -e. And that gives you the preprocessor output. So it's not actually compiled the code into assembly language or into machine language. It's just added some information. So it's going to be linklist.c. And then I say vim l.text. And so you can see it's added some commands here at the start, like we got built-in command line and some other stuff. Simple enough, right? So I'm just going to exit out of there. And then I'm going to go include standard IO. So this is the standard input and output library for the C. So I'm going to write that. And now I'm going to do this again. And now when we open it up, we got all this junk. It goes on for a long, long time. So you can see here we finally got to the main. So all this other stuff before, the C preprocessor, all it does is copy and paste into your file the contents of standard I/O. So that's all that's happening with those include statements. And if you use define statements, that's part of the preprocessor as well. So it's just interesting to see that. Maybe I'll show you one other thing. So I'll just get out of here. And if we go -s and I'll say ll.asm, we can see the code that I've written compiled into assembly language. So just open that up in a text editor as well. We'll just go ll.asm, and we've got the machine instructions here. It's pretty cool. Anyways, though, we better get onto the linked list stuff. So with our linked lists, we're going to include we're going to start with a struct. So this is what I talked about previously. So we're going to say a type def struct node, and this is defining our own node type, which is useful because if we didn't do the type def, we'd have to write struct node each time. So it's just a nice way of reducing how much we have to type. So then I'm going to declare a couple of member variables inside the struct. And interestingly, since we're inside of the struct and we're referring to a pointer to a struct node, we have to actually write struct node this time. We can't rely on the type def because it's kind of like you're already inside of it, so you can't do that. So we're going to create a pointer to a node. So if I want to start the list, I'd create a head node. So I'm going to say it's actually a reference to the first item in the list. So it's a pointer, it's a variable which stores an address to a node. And we're just going to declare it as null for now. So if I want to actually create a node, for the linked list, we're going to be using malloc. So actually to include malloc, we'll have to say include standard library. And then we can do malloc. So we're going to say head is equal to malloc. And then size of is a keyword that gives you the size of the data type. So you could use it for an int. It'll give you the size of an int on your system. You could use it for a char and it'll give you 1 byte in all cases. Or you can give it the size of your node, which is the size of the aggregate. So it's the size of the int plus your pointer. So you're going to go size of node. And then malloc is going to return a pointer to the place in memory that it's allocated some space for a node of that size. So after that's done, we can refer to the member variables of the node. So I can, because it's allocated on the heap, we'll use the arrow notation. So I'm going to say head data, arrow, or head data, whatever, is equal to 0. I'm going to say head next is equal to null. So let's see what happens. I'm going to say gcc-o linked list. So this is the linked list is our output. So -o linked list, and then linked list.c is our actual code. And so it worked. And if I want to see the result of that, I can say printf, which is just a it's a function call to the standard IO library. So I'm going to say the address of the node. So this is just the format way of formatting things in printf. So we're going to say %p, and then I'm going to say data, %d for your number, for your integer, and then I'm going to say next, and that's also going to be a pointer. So I'm going to say %p, and /n just means new line. So then we're going to have head, and then we're going to say head data, and then head next. So let's print that out. Oops. Oh, I don't think I... So as we can see here, this is the address in memory of what head points to. So this is the first address of this struct. C knows how big the data is, so it knows how far along to go to get to this element, because within the node, the data is stored sequentially. So then we say data 0, and it prints that out, and since we said this is null, it prints out nil. So that's just showing the very basics of how to do this. So we have a bunch of functions that we'll want to create. So we want to have a create node function, print node. We'll want to print the whole list. We want to prepend the list, just means to add to the start, and then append list, just to add to the end. And I think that's all we're going to do. But there's a lot more you could do. But this is just a basic idea to get you started. Also, what we should do, if we wanted to delete a node, it's quite complicated, so you'll have to think about it, but we have to do this, which is say free, and then the pointer that points to the address that we're freeing. So when we call free, that'll deallocate the memory that's been allocated by malloc here. So we'll just run that, make sure it works. So we don't see anything, so it's all good. So if we want to create a node, we're going to say node star, which means that this returns a pointer to a node. And we say int value. And node next. So we're just going to do what we did in the main function. So we're going to say node temp is equal to malloc size of node, and then temp data is equal to the value we're passing in. Temp next is equal to next, and then we're returning temp. Remember, if this was just any old variable that we created in the function, we should not return it from the function because it will be on the stack. But since we've called malloc, it's on the heap, so it's okay. We're just returning a pointer to it, and then we're going to assign it to something. So this is okay. Don't worry. So let's just test that out. So I'll get rid of this. And we'll say node star my node is equal to create node. So this is just a variable which stores an address to the node that we created here. So we're returning that address from the function. So we're going to say, oh, let's just do 1. And then we're not going to give it a value for now for the next next pointer. And okay, I think that's good, but we probably want to print that out instead of having to write that every time. So we'll do the print node function. So I'm not going to return anything, so we'll just say void and then say node star my node. So we're going to pass in a pointer to a node, and then we're going to say if the node is null, or if the node is not null, we're going to print it out, print out the values. And if it is null, then we're going to say the node's null. Actually, I could just copy and paste this, so I'm going to go down here. I'm in insert mode on Vim, so I'm going to press escape, and now I'm in, I think it's called view mode. I'm going to press V, which means visual mode. When I press V, then I can select this, and I'm going to press Y, and it just copies it, and then P, and paste. So I need to do that. And if I want to scroll back and crosswords, I can hold shift and then press the arrow keys and I can get back quicker. There's probably other ways to do this, but you just got to learn as you go. So, and then escape, colon, W means I just wrote that. So now I want to print the node. So my node. Oh, I think I made a mistake here. Oh, I just forgot when I was copying and pasting this that I have to change this. Good idea. So my node. There's better ways to do this in Vim. I'm still learning as I go, but I could have probably changed all of those at one time. So write this. And so now we have, we're printing this one, which is the head, and then we just printed the new node that we created. So obviously nothing is really linked together yet. But we're going to implement that in our append and prepend lists. So let's do the prepend, or let's do the append list. It's the more complicated one. There's also many different ways you can do this. This is not necessarily the best, but it's just to get you guys thinking. And there might be mistakes in the code too. So if you can find them, you get some bonus points. I don't know what the points are going towards, but you get them. So I'm going to create a node using the function that I just made. So I'm going to call it temp value null. And then since we're adding to the end of the list, we want to create some kind of a pointer. I shouldn't use the word, it is a pointer, but we want to have some way of keeping track of where we are in the list as we iterate through it. So I'm going to create a node called cur. And like I said, this just goes along each node in the list one by one and points to them. And we update its position. So we say if head is null, then head is equal to temp. Else, while cur next is not null. So while the next value of current is not pointing to a null value, we're going to keep iterating through the list. So we say cur equals cur.next. So it's just looking at the next value of the node and changing its value to that. So it's just gonna go through the list. And then once we've got to the end, we say cur next equals temp. So I think that's good. So we should go down here and test it out. So I'm just going to get rid of some of this. Oh, actually, you know what? Before we do that, we should implement the print list function. So it's pretty much the same as what we just did, except as we iterate through it, we're going to print out the value of each node. So I'm going to say print list node star start node. I mean, naming is not very consistent, but doesn't matter for now. So cur is equal to start node, say if start node is null. There's lots of edge cases of how everything can go wrong, so you're going to have to consider that when you're writing. And there's also ways, like if this was actually null, I could return a value. I could have the function return like a -1 or something. It really depends on how you want to do it. So it's really just the same as what we did actually. Except we're saying cur is not null instead of cur.next. You might want to think about why you might want to do things like that, because you're going to run into problems if you go beyond the bounds of the list and things like that. So we're going to print the node at each iteration of going through it, and we're going to update to the next one. So it should be good. So I think we should get rid of some stuff. So just using escape, and then pressing V to visual, and then I'm just going to hit delete, get rid of it. And then let's see, append list. Let's add 4 just so we know where we are, or we know what the value is. And head, and then we're going to say print list, and hopefully this works. So press escape, colon, and then W to write. I'm going to go over here, compile it. It worked. Hopefully there's no segmentation faults. And so it works. We can just, this is just the head printed twice because I have that printf in there. But this is the value, this is the address of the head node, this is its value, and this is its next pointer. And we can say that we can see that this address is the same as the address of this one. Okay, so then this stores the data, and then its next pointer is nil, meaning it's null. So if we wanted to test this, we might say, might do a little for loop or something. You should really, if you were writing an actual linked list, you would have your linked list in one file, and then you'd have your main in another file, and you would use a include header file, which lists all the functions in your linked list, and then you would write a bunch of tests for all of your functions. That's like the best way to do it if you're really going for it. So append list, and we're just going to say I head. And I'll get rid of this. Another way, another little shortcut in Vim, if I press escape, so I'm out of the edit mode, and I press D real quickly, twice, it's just a delete. So I just deleted the whole line. So escape and write it. So now we can see we got this whole list. And each of these points to the address of each following node. So it's pretty cool. And then we just have one other function to implement. So this is the prepend. And the way I did it in this case is kind of interesting because we have a pointer to a pointer. So it's a variable which stores an address to a variable which stores an address. So as you can see, the pointers can get complicated. But the reason I did this is because I want to access the pointer from within the function in a different way. So say node star temp is equal to create node. I'm just creating another node here. I'm adding it to the start of the list. And I'm saying star head is equal to temp. So I'm actually updating the address stored at head to be pointing to this new one. That's why I use the double pointer there. So then if I want to prepend the list, let's say prepend, and we'll get a value that's unusual so we can see it. And then because it's a pointer to the head, we have to do that, which is saying the address of the pointer. It gets complicated, but you'll have to think about this sort of thing. And so at the very start, we now have 42. So let's see, let's do another for loop. Let's start it at 10. So since we can see the results here, and since we're adding to the start each time, it goes backwards. So we added 10 first, and then 11, then 12, 13, 14, 15, 16. And then we can see this node points to this node points to this node, etc. So I've shown you guys the very basics of how you might think about some of this, but what you're doing is quite a bit more complicated. But hopefully this will help a little bit. So thanks for watching.